thank you, the organizers, for the invitation. I will try to take you to another dimension, the third dimension.
The fourth day.
The fourth dimension, we will have a bit of fourth dimension as well, so we will see. Well, as outlined in the abstract, I would like to contribute to what seems repeating questions over the years. Are we there yet? Have we managed to harvest the possibilities of 3D GIS in archaeological excavation? For an answer, I will try to move quickly from a description of the present state of the art to a review of the dimensions of the archaeological archive and the possible ways it has been implemented in 3D GIS. I will then talk about the analytic and synthetic possibilities opened up by 3D excavation archives and discuss also the limitations that we experienced in realizing the analytic potential of their informational capacity. This will be further explored with respect to research implications and possible things to be explored for linking documentation with data usage. Last year, the first handbook on archaeological 3D GIS came out, where the authors, Nicolo Delundu and Giacomo Landensky, provide a comprehensive account of the current state of the art. They try to advocate that 3D modeling products are not an end in themselves, but rather the means for augmenting our analytical possibilities. They describe a disciplinary shift from visualization to simulation and gradually to the eventual transformation of archaeological practice in the digital realm. They highlight this aspect through the thorough discussion of 3D GIS mapping, the presentation of standard workflows or pipelines for achieving 3D GIS data, and several examples, including excavation-based case studies that present a strong case for the analytical potential of 3D GIS. However, we may still be some way from harvesting the full capacities of GIS in excavation research. There are still very few working examples that move beyond the documentation, representational, and managerial aspects of 3D GIS and delve into their analytical potential within post-fieldwork knowledge building workflows. Numerous questions, like the ones included in this slide, are still open, such as a solid appreciation of the informational benefits of 3D GIS, the potential ways 3D representation can act as an entry point for the investigation of the spatial information of an excavation archive, analytic workflows that move beyond the representational benefits to data analysis, issues of workflow standardization and alignment of digital knowledge production processes with the excavation process, possible changes that are required during data collection or excavation fieldwork to harness the powers of 3D GIS, all the way to the social and organizational implications with respect to applying 3D GIS data procedures or the legitimacy and sustainability of both data and interpretations made through 3D GIS tools. To explore some of these questions, I will try to present some of my experience from working with 3D GIS excavation data. Examples will be drawn from 3 archaeological projects that provided a testing ground for an early working example of a 3D GIS workflow for excavation research, which informed similar approaches in Greece and beyond. The 3D workflow was developed in relation to the Neolithic excavation of Palliambela Kolingros and has since been applied in subsequent projects such as the cave of Agia Triada in Charistos and the prehistoric site of Thessaloniki Tumba. During development with Kostas Kotsakis and colleague Spiros Spidis, we envisioned a workflow that would provide, in essence, a digital place or simulation environment for building knowledge by exploring spatial, temporal, and thematic associations between excavation data. However, in many ways, the knowledge building aspect of our effort remained largely underexplored. Recently, as part of the Ariadne Plus project, we were presented with a chance to reassess part of the Palliambela Kolingros archive for the position, but also reflect on the digital knowledge production processes using 3D GIS environment. Let's take a closer look. When it comes to 3D modeling, distinct geometric types can facilitate the representation of spatial data generated during excavation. I show here the different geometries that we used in the past. Individual finds or samples can be depicted as points, while volumetric entities such as contexts or layers can be represented as 3D bounded polygons. Surfaces can be generated using either DTMs or tins, which can be draped with photographic textures and used for delineating objects of interest on top of them with polylines or polygons. Designated surface boundaries of individual architectural features, such as the cut of a pit or the surface of a wall, can be produced through direct modeling procedures. In the last decade, the advent and widespread use of image-based modeling, as well as the recent implementation of volumetric representations, have provided additional geometric types. 3D meshes have been essential in improving the shape accuracy of excavation surfaces and achieving enhanced photorealistic results. Voxels, on the other hand, have been instrumental in depicting geophysical data or enhancing and combining legacy data from older excavations, but otherwise remain underused in excavation research. The spatial entities defined above provide the main entry points to the variety of observations and other documentation media that are created during fieldwork. For each of these observation units, certain attributes and interpretive descriptions are recorded by the excavator or the specialist during fieldwork. All of these provide the thematic aspect of the relevant information that needs to be linked to the respective spatial entities recorded. Another aspect of an excavation information is related to time. We identified at least 6 different timelines for every archaeological object. Some of them are related to direct observation in the present, like the time of retrieval or data entry, while others may be calculated at a later stage, like the absolute or relative chronology, or get populated after association with other excavation objects. Like, for example, a find may inherit the chronological attributes of the layer within which it was found and vice versa. All these temporal attributes can be stored as timestamps of different kinds, either points or temporal durations, and explored using Allen's operators. So in a sense, the key to 3D GIS usability is the integration of excavation entities in a single cartographic background, using all sorts of 3D geometric types that act as gateways to the complete visualization of descriptive and chronological information. Features that have been documented subsequently, and usually over different excavation seasons, can be integrated, visualized, and explored together in 3D. Through an informal visual analysis that employs standard navigation and graphic solutions, useful observations can be directly extracted and used for archaeological interpretation. Here you can see different types of excavation data, their spatial combination, data classification by different variables, and object identification. So you can see how you can access all excavation just by clicking, using all the relationships within the database. However, 3D representation must also be supported by the underlying excavation information. In this example from Thessaloniki Tumba, several contexts have null pottery chronology values, while in the remaining, the existing chronological information is unnormalized, impeding comprehensive data classifications. Geometries may also be wrong due to data input errors, but this can only be revealed after visual inspection, after construction visual inspection, and requires corrections and reprocessing. This means that when turning excavation documentation to 3D, a certain effort should also be directed towards control over data input, or at least cleaning and normalizing the respective excavation data we want to visualize. In 3D, data gaps become even more evident. preventing datasets from being used in explorative data analysis and pattern recognition processes. Another problem is the substantiation of interpretations made while exploring data in 3D. In some cases, an interpretation can be the result of a simple visual assessment that exploits the possibilities of thematic information and spatial association. In this example from Palliambela, the soil texture values recorded in different contexts during excavation provide a possible indication for the inward fall of the clay wall superstructure in relation to its foundations. How do we link these interpretations with the actual data we use to make them? How do we store such an argument within a database or link it to the evidence used to make such an assumption? Can we pipeline digital argumentation processes? Further issues are related to the availability of alternative processing workflows that result in different 3D outputs with variable spatial accuracy or visual affordances. In this slide from Palliambela, different representations of the same excavation area are shown. At the top, a series of Neolithic pits and ditches are visualized with the respective stratigraphy as orthophotos on DTMs or TINs and as vectorized features. At the bottom, you see the 3D texture mesh model of the same area. Itself, the product of retrospective modeling, the photogrammetric modeling of archival footage. What's at stake here is the legitimacy and reproducibility of our digital interpretations that are based on evidence of different processing outputs. What do we keep as evidence of our interpretations? The vectorized features, the textured mesh, the point cloud, the images, all of them. Further considerations of this observation is also related to the need for the formal analysis of excavation data in 3D. How can we use 3D datasets apart from visual classifications? Back in 2008, we experimented with simple 3D distance queries and the creation of artificial sections. These functions have either been integrated within standard 3D GIS toolset or grown to be more interactive. However, in the former case, usability is largely limited to points, while in the latter, it reproduces a 2D analytic mentality involving planes and projections. Can we envisage new analytical workflows for 3D data patterning? Further considerations are related to the socio-technical arrangements necessary for deploying such tools in excavation research. In the case of Palliambela Kolindros, we soon realized the difficulties in feeding the system with data, using it for analysis, and preserving its usability. Evidence for versioning issues were noted within the first 2 years of development. Cycle completion. A custom interface designed for improved and easier interaction with the data content soon became obsolete. Photogrammetric procedures for 3D data modeling was introduced, but its products were not integrated with the rest of the data infrastructure. Digital data feed continued, but was never completed in full or vetted. In all, maintaining both the 3D workflow and the data has been very difficult in terms of both institutional, like the maintenance of infrastructure and the digital competence, and operational capacities, the integration of new procedures. By 2018, the project had a partly outdated system, moderately fed with data and with little analytical contribution. All these, to my opinion, showcase some of the obstacles with respect to 3D GIS usability in excavation research. Substantial effort and technical support is required to create a 3D GIS excavation archive and employ it for interpretive gains. Data creation and maintenance requires infrastructure, backup solutions, dedicated staff. Data documentation, recording, and geometric registration are procedures far from standardized. Many of these observations are about the people who would be using 3D GIS and all this painfully compiled data. Who are they? What do they want to find out? Are they even close to having the necessary knowledge for using these tools? The list could go on. However, all these points primarily point to a difficulty to conceptualize digitally assisted interpretation procedures. We are getting increasingly good in producing 3D data, but we still haven't figured out exactly what to do with them. I will now turn to potential research avenues and that may provide some answers. A possible step is to exploit recent advances in 3D topological functions and combine different tools into 3D processing pipelines. In this example, coordinate measurements from individual contexts can be used to model deposit aggregations formed by grouped contexts. Using the minimum bounding volume function, a bounding surface is generated using only the outermost coordinates and disregarding the innermost. To remove overlaps between individually modeled layers, 3D intersections are determined between layers and used to calculate the difference to produce 3D geometries that do not overlap. This modeling workflow can be pipelined as a geoprocessing model, which can be stored, documented, and recorded. So we need to test new functions, but we also need to start documenting their use. Recent advances in geospatial analytic procedures should also be explored. In the cave of Agia Triada, we found evidence of a relatively ephemeral burial episode that included dispersed human bones in yellow, pottery in red, and organic material in green. We placed the digitized drawings in their 3D position and marked the spots of individual items, bones, pottery, and organic samples with points. These were initially plotted and inspected with a stratigraphic section to indicate general trends with respect to vertical distribution. In addition, we recently employed 3D interpolation procedures for creating a voxel grid to provide a volumetric distribution of the material and detect local variations. So you say now that we can, with the voxel, we can detect the distribution of all this material, both in all dimensions. Obviously, if we are to base our interpretation on these results, we certainly need to keep both the original data and the analytic settings and parameters for referencing or reprocessing. We may also try to understand the semantics of 3D GIS creation and interpretation processes. In this example, I employ concepts from the CDOC CRM ecosystem to describe the creation and interpretive usage of a 3D feature. During excavation, a stratigraphic volume unit is removed. The action reveals a fixed physical human-made thing, a wall, for example, with certain properties, such as feature type, building material, and dimensions. At the same time, this feature acts as a stratigraphic interface that confines the volume unit that was removed. This feature is spatially defined by coordinate measurements. These are employed in a digital machine event, perhaps with many processing steps, that creates a data object. Forming its representation. This data object is employed within GIS in subsequent group declaration event processes to link the original feature with wall components from the next range into a stratigraphic building unit that forms part of the same designated house or built wall. In this respect, I try to acknowledge that in digital knowledge building workflows, as we move on to later stages in post-excavation studies, we increasingly use digital datasets that substitute the material reality that was initially encountered in the field. Using semantic modeling, we may streamline and link interpretations with the respective digital processes and data. Finally, in digital pedagogy, there have been some interesting recent initiatives. The Erasmus Plus Minerva project set out to improve and facilitate the learning of geosciences applied to cultural heritage through the coordination of an online structured course. Similarly, the Delta project tried to map digital literacy in archaeological curricula and fill some of the void by designing a course that combines the physical space of an archaeological excavation with a digital space of online learning. Finally, in the context of the Ariadne Plus project, emphasis was placed in the semantic mapping of excavation data to provide developers with a better understanding of the benefits of data modeling. In my opinion, these three projects showcased to a great extent the path for obtaining a new generation of GIS practitioners in excavation contexts. That is data modeling, geospatial skills, and excavation training. To conclude, I think we are still experimenting with the possibilities of 3D GIS in excavation research. To overcome some of the issues outlined, we need to start thinking of new ways to tailor 3D GIS procedures for use in the context of archaeological excavation research. To do this, we first need to conceptualize digitally mediated data and knowledge production procedures and black box digital practices through the linkage of data processing with data usage, and elevate the importance of streamlining geoprocessing functions by linking these to the way they are employed in archaeological argumentation. To do this, we must educate a new generation of archaeological practitioners, and in this respect, I'm very happy for the Aegis initiative and the opportunity to engage in interesting conversation. Thank you.